This is the roadmap of the talk. It's divided in these 5 parts. First of all, I introduce a brief history about the representation of partially ordered set. Then I introduce the equiposet and present the curricular representation of equiposet. Later, I present the lifting algorithms which permit build the Auslander-Reiten Quiver for some equiposet and some references. The main goal of the talk is present this algorithm, this lifting algorithm, which permit to build the Auslander-Reiten Quiver of some equiposet by means of one ordinary poset. Well, remember that the representation theory of a partially ordered set was introduced and developed by Nazarova, Reuter, and their students in the seminar of Quiver. And they introduced this new theory with the goal to study the Brauer and Troll conjecture regarding classification of algebras. To solve that conjecture, Nazarova and Reuter introduced one algorithm of differentiation called with respect to one maximal point. And with this algorithm, Kleiner classified poset of final row representation type. For this algorithm, Gabriel, 1 year later, proved that this algorithm established one equivalence between 2 suitable categories between the representation of the original poset and the representation of the derived poset. And we need to do the one suitable quotient of categories. For this reason, the algorithm of differentiation is the main tool to do the classification of the ordinary poset and the poset with additional structure. Also, this algorithm was used by Nazarova to do this criteria for classify a poset in 10 representation type. Later, Zavadsky introduced another kind of algorithm of differentiation. This algorithm is called D1, and this is one algorithm which is more general than the algorithm introduced by Nazarova and Reuter. And Zavadsky and Nazarova gave this criteria to classify poset of final row representation type. Remember that one poset, this is a not empty set, together one partially ordered relation. For instance, this is one example of one poset. Here we have 4 incomparable points. This is another example. Here we have 3 incomparable chains. Each chain is a linear ordered set. This is another example of poset, and that is the theorem given by Nazarova and Zavadsky to classify poset in finite row representation type. And this is an easy theorem because you just need to check that the poset does not contain a subposet, this poset that we have here. All this theory of ordinary posets were developed in the 70s and 80s. And after they introduced a poset with additional structure, that structure, the more developed structure was the equiposet, that poset with involution. All this kind of poset was studied by Bondarenko, Nazarova, Reuter, Zavarillo, Zavadsky. This is the original definition of one equiposet given by Zavarillo and Zavadsky. And we start one poset. Here is one actualization of this definition also given by Zavadsky and Rodriguez. And if you have one poset, we say that the poset is called a quiver if all the relation is divided in two different relations, one strong relation denoted by this symbol, and one weak relation denoted by with symbol. And that is the main condition that satisfies the equiposet. Say that if you compose one relation, one strong relation with another relation, then the composition is strong. Also, we can associate by diagram to one equiposet. Here, this point is to denote the strong point. This point with tensor is to denote the weak point. If these two relations are a strong relation because are related with this strong point, here are subset of the poset. Here, all points here are weak. This point is weak. Then this relation is weak. But here, as we have double line, this double line means that we have one strong relation between this weak point and all point here. So the correlation with the representation of equiposet with the representation of the ordinary poset is analogous to the correlation of representation of the value graph with the representation of the ordinary graph. So we have the classical representation theory of poset. This classical representation theory is over one field, F, and the representation of the equiposet is over the one pair of field F and G, where G is a quadratic extension of the field F. This is the minimal polynomial when we do the quadratic extension. Here U is one root of this minimal polynomial. Then, as in the classical case, that we can have the complexification of one R space. Here, if you have one, if U sub 0 is one F space, you can do the complexification, and is denoted by U sub 0 tilde, and this is the form what do the complexification of this space. Then, in this form, here U sub 0 is a G vector space. And we can associate all these space, if you have one, if double is one subspace of U sub 0 tilde, then we can associate all these three subspaces, F subspaces. Okay. If you have one equiposet, you have the pair of fields F and G, you can define one representation of the poset. One representation of this equiposet, this is the system of vector spaces in this form. Here, U sub 0 is one F final dimension vector space. And for each point in the poset, you have U sub x. U sub x is one G subspace or the complexification of U sub 0. This representation is attached to the order relation in the poset. Here they satisfy this condition. If you have this relation, then you need to disperse these contents. And that is the object of the category of representation of the poset. One morphism here. If you have two representations, U and B, one morphism in this category, this is a morphism, a linear F-linear map between these vector spaces. And this morphism satisfies this condition here. This is the natural complexification of the linear transformation. Here, in this category, we can define the sum of representation in a natural way. You have two representations here, U and B. You can do the sum. This is do the sum of the main here spaces, U sub 0 and B sub 0. And for each point, you can do the sum of the corresponding vector spaces associated here. You say that, or we have that one representation is equal to 0 if all spaces associated to the representation are equal to 0, right? Then if we have a representation which is not equal to 0, this representation is called indecomposable if always that you can see the representation at this sum here, one of the sums is equal to 0. Then with this condition, the category of representation of partially ordered set, this is a Krull-Smith category. This is a abelian category. Here, Krull-Smith category is that all representation satisfy the unique decomposition as sum of indecomposable representation. Nazarov and Reuter translate the conjecture and Brouwer and Troll, and they transfer all different information to matrix problem, language of matrix problem. After they translate this information to the Posets theory. For that reason, the equiposets also have one matrix problem. Here, one matrix representation associated to one poset. This is this matrix that we have here. This is a matrix which is divided in vertical stripe. Here, the entries is over the field G if the point is a weak point, and the entries here is over the field F if the point is a strong point. If you have one relation between the points, you can do a linear transformation of the column in this stripe to the column in this stripe, right? Then you have the matrix, you have one admissible transformation, and this is the matrix problem associated to the equiposet. Then, which is the main problem regarding poset with additional structure, is to given a complete description of indecomposable representation and classify all irreducible morphisms in the category of representation of the poset. For instance, here in particular for the equiposet. Let me present some kind of indecomposable representation, which is our class file. For instance, here PMP is a projective representation. You put here F in U sub 0, and for all points in the poset, you put the 0 space. This is a notation given by Gabriel, and this is the notation in the matrix form. This is a matrix representation. If you have one weak point, you can associate this representation. This means that here U sub 0 is equal to F squared, and you put the span of this vector in the point A, and all upper cone of the point A. Here, for instance, you have two incomparable points. You have A is weak, C is strong, and you have these two representations associated to this kind of situation. And this is an indecomposable representation here. For instance, if we have that poset, here we have one weak chain with this point, the point 1, 2, 3, 4, and 5. These points 6 and 7 are strong points, that these relations here are strong. Then the indecomposable representation T1 here is have here U sub 0 is equal to F squared, and this is the span here associated to each point here. And as this relation is a strong relation, we take here the complexification of the U sub 0 here, which is F squared. The complexification is G squared. This is another indecomposable representation here. P4 you put G as vector space in the point 4 and all upper weak point here. And in the point which are not related with 4, you put the vector space 0. And the point which are less than or equal to 4, you put also the space 0. Well, that is a kind of representation. Sabatsky defined one form to associate to one equiposet, one ordinary poset. This poset is called the evolvement of the poset. You have here one P is a one equiposet. P hat is one ordinary poset. How do this? The strong point remain without changes, and the weak point, to each weak point here, you associate two incomparable points called x prime and x double prime. And all these points satisfy this relation here. For instance, if we have the same poset, as this is a weak chain, then we divide this weak chain in two incomparable chains here, the chain prime and the chain double prime. This is a strong point. This point remains without changes. And as this is a strong relation with the point 3 and 6, then 6 is greater than or equal to 3 prime and 3 double prime. Right? This is the evolvement of that poset. To classify a poset with additional structure, Sabatsky defined 17 algorithm differentiation to classify ordinary poset, poset with involution, equiposet, and equiposet with involution in that form. This is one result given by Sabatsky, which he gave the representation of the equiposet by means of the representation of his evolvement here. Right? This is 10 if the evolvement is 10, or this is wild if the evolvement is wild. Also, this is a equivalent condition for this poset. One poset is of final Gauss representation type if this evolvement is of final Gauss representation type, or if the poset is not wild and does not contain one of these posets as sub-poset. Sabatsky, following the ideas of Gavíria, give the categorical properties of the algorithm differentiation D1, and by means of this algorithm differentiation, Sabatsky described the structure of the Auslander-Reiten quiver of the ordinary poset of final Gauss representation type. This is in general is not easy. What we want to build the Auslander-Reiten quiver or associate to the category of representation of one poset, because the Auslander-Reiten quiver associate, this is a form to compress all information of the category, because here in this quiver, the point is the isomorphism class of the intercomposable representation, and if we have one line between 2 points, if we have one irreducible morphism. Then here we have the lifting algorithm to build the Auslander-Reiten quiver associated to some equiposet. In the ordinary case, the Auslander-Reiten quiver is just one quiver, and in the case of the equiposet, the Auslander-Reiten quiver associated to the category of representation of the equiposet, this is a Value quiver. Value quiver, this is the evaluation of the arrows in the Auslander-Reiten quiver. This means this dimension here, or the reducible morphisms here. If that dimension is equal to 1, then we don't put 1, 1, just don't put the evaluation. And we have just this situation in the Auslander-Reiten quiver. The evaluation is equal to 1 or 2, or 2 and 1. Then, if we have this rotation, we put just this number here. This is just by convention. Then, the lifting algorithm is, we consider this algorithm. It is described in this form. The algorithm, how it functions. You have one equiposet, you associate the ordinary poset, which is the evolvent. This is the second point here. And the ordinary poset, you compute the Auslander-Reiten Quiver. With this Auslander-Reiten Quiver of the ordinary poset, you do some operation and you obtain the Auslander-Reiten Quiver to a quick poset, right? This is described. This is some properties of these algorithms. For instance, here, the representation here P empty remain without changes by means of this algorithm. Here, if you have these two representations, remember that x prime and x double prime coming from one weak point, then this representation passes through the lifting algorithm, obtain this indecomposable representation in the equiposet. And this is two indecomposable representation in the ordinary poset. Well, one example to understand better from this lifting algorithm. Here we have one equiposet. This equiposet has just one point, one weak point. Then we need to compute the Auslander-Reiten Quiver of this poset. So you calculate the evolvent of this poset, separate this poset in two incomparable posets, one prime and one double prime. You compute the Auslander-Reiten Quiver of this poset, ordinary poset. This is the Auslander-Reiten Quiver. Here, as this point coming from one weak point, then you need to do the sum of this number. Here, this number means the dimension, here the dimension of u sub 0, and this the dimension of u sub 1 prime. This is dimension of 1 double prime, right? Then you do the sum 1 plus 0, 1 plus 1, 0 plus 1, 0 plus 0. You just do the sum of the point which coming from one weak point. Then here, you can see here that this vector dimension is equal to this vector dimension. Then you glue this vector dimension with this vector dimension here, and you obtain this element here. And here you need to divide the dimension here by 2, also here by 2, because you are gluing these 2 points. And you obtain this Auslander-Reiten Quiver here, and this is the Auslander-Reiten Quiver of this equiposet. Yeah? This is the form which is our computing the lifting algorithms. Here also we have another example. The main here, you need to focus in the weak point here. These chains are dividing these two chains. Yeah, we need to do the sum of just the coordinate associated to the weak points, right? Here you can see that, for instance, this vector dimension is equal to this vector dimension is equal to this vector dimension. Then you need to do the sum of the dimensions which are equal. And we continue with this procedure, and we obtain here the Auslander-Reiten Quiver of that equiposet. Right? Then this is the Auslander-Reiten Quiver of this poset here. This is another example. All these posets here are of finite representation type. But the same procedure, we can do the same procedure to obtain not all Auslander-Reiten Quiver, just the pre-projected component and pre-injected component to the poset which are infinitely representation type. In this example, we have here K6. K6 is equal to 2 weak incomparable points. If you do the evolvement of the poset, you obtain the tetrad of 4 incomparable points. This is the pre-projected component of that ordinary poset, and you pass this pre-projected component through the lifting algorithm, and you obtain this projected component of the equiposet. This is the evaluation here. And also we can calculate the projected component of the poset. Here, to obtain a result of that procedure, we obtain these 2 two theorems, which say that if we have one sincere equiposet final representation type, then this is the Auslander-Reiten quiver of that poset, right? And if we have these two kind of equiposet, the K6 or K8 are two infinite representation equiposet, then we can compute the pre-projected and the pre-injected component of this poset here. Well, this is some reference, almost all reference coming from the Quiver School of Ukrainian mathematician. Well, thank you so much for your attention.
Are there any comments or questions? No comments, no questions? So let's thank Isaías again. Okay. Thank you. And we resume in 4 minutes.